Hi everyone, welcome to SuzaCon Digital 2023. So the topic for this session is platform-aware machine learning pipeline optimization and performance enhancements using Rancher, RK2 and other open source technologies. Before we start with this session, I would like to introduce the team. My name is Mihir Patil. I'm currently working with OS3 Infotech as Senior Systems Engineer, specializing in implementing the open source technologies and focusing on the deployment and integration of Rancher with other open source technologies. I've been accompanied by Mrutyunjay Sahu, Systems Engineer at OS3 Infotech, having expertise in implementing pipelines for the machine learning workloads on the Kubernetes infrastructure. Now, the agenda for this particular session is broadly divided into 7 sections. We'll start off with the introduction and the problem statement, and then discuss about the solutions overview and architecture. We'll also throw some light on the technology stack that we have used for this particular demo. And then Mrityunjay will explain the architecture and the flow for this demo, followed by the demo itself. And then we will conclude this session with the real world use cases. Now, this particular solution leverages Rancher, RK2 and various other open source technologies to address the challenges of optimizing the platform-aware ML workloads within a Kubernetes cluster. We will walk you through each step of this solution and showcase how it enhances the performance and efficiency of the ML workloads. Now, discussing about the problem. In the Kubernetes landscape, the cluster comprises of multiple master and worker nodes. The worker nodes can have various type of hardware specification. While some workloads in the cluster may not require specialized hardware to run, ML workloads on the other hand benefit from the dedicated hardware designed for rapid data processing. Therefore, it becomes imperative to leverage the hardware capabilities and enhance features of different worker nodes within the Kubernetes cluster to optimize the machine learning workloads. Unfortunately, Kubernetes lacks a native mechanism to identify and schedule the workloads on these specific nodes with specific capabilities. This limitation hampers the business from fully harnessing the platform's potential and achieving optimal efficiency for the particular machine learning workloads. Also, considering that machine learning workloads can be costly to run, it is crucial to optimize their execution to avoid unnecessary expenses. Given that machine learning workloads often demand substantial resources, scheduling them on the appropriate nodes become essential to avoid poor performance. Now, as you can see in the diagram, MLOps is nothing but a set of practices and techniques that combine the principles of DevOps with the machine learning workflows. It focuses on efficiency, integrating the machine learning model into production systems and managing the entire life cycle of that particular model. Now, talking about the technology stack, the Rancher management server plays a crucial role in managing downstream clusters that are running the containerized workloads. Through Rancher, we have deployed an RK2 cluster that is running the platform-aware machine learning workloads. To further exploit the capabilities of the worker nodes within the downstream cluster, we have implemented node feature discovery. NFD helps to identify and utilize the specific features and resources provided by the worker nodes, optimizing the execution of our ML workloads. In order to maintain a centralized code repository for version control and collaboration, we have chosen GitLab. GitLab offers a robust platform for storing and managing code for seamless collaboration among team members. To streamline the process of building and deploying our ML workloads on the Kubernetes cluster, we have integrated GitLab CI/CD. This automated flow enables us to efficiently build and deploy our ML workloads, reducing manual effort and ensuring consistent and reliable deployments. Lastly, to monitor and visualize the performance and enhancements achieved through the optimization of our workloads, we have implemented Prometheus and Grafana. These tools provide valuable insights into the performance metrics of our ML workloads, allowing us to compare and analyze the difference between optimized and non-optimized scenarios effectively. Now, I will be handing over the presentation and demo to Mrutyunjay. He will continue with the architecture flow and the demo, guiding you through the rest of the session. Thank you all. Over to you, Mrutyunjay.
Hey Meher, thank you. I appreciate your introduction and valuable insights you have shared so far. I will take the lead and will continue the session by showcasing the live demo. My name is Mrutyunjay Sahu and I am a systems engineer here at OS3. Let's explore the architecture and flow of our platform. To visualize this, we have created an animated architecture diagram that demonstrates the flow of the demo and how each component interacts. The architecture diagram consists of three main components. The GitLab server serves as the source for our code repositories and also triggers the deployment process. Then we have the rancher management server, which is responsible for managing downstream RK2 Kubernetes cluster and its workload. At last, we have the RK2 Kubernetes cluster consisting multiple Kubernetes master and worker nodes. Let's dive into the animation that demonstrates the flow of the demo. In first step, we cordon off all the worker node with the hardware multi-threading capability. Doing this helps us to prove that the MLOps workload will only be scheduled on the nodes with the desired capabilities. In our case, hardware multi-threading. In second step, we trigger the platform-aware MLOps pipeline from the GitLab server. The workload is optimized to leverage some CPU features like hardware multi-threading. In third step, we see that the workload remains in pending state. Since we have cordoned off all the worker nodes with the hardware multi-threading capability, the workload cannot be scheduled on any rest of the nodes. This step highlights the platform awareness of the pipeline. In third step, we showcase the process of uncordoning a single node with hardware multi-threading capability. Uncordoning this node, it allows the workload to be scheduled on that node exclusively, taking advantages of its hardware multi-threading capability. Through this flow, we showcase how our platform optimize the scheduling of the workload, ensuring that they are placed on the node with the required capabilities for enhanced performance and efficiency. In addition, we also schedule a non-optimized platform-aware workload using the same approach. Triggering the deployment of the non-optimized workload follows the same flow as we did for optimized workload, specifying requirements for it to schedule on the nodes with the hardware multi-threading capability. So we cordon off all the worker nodes with the hardware multi-threading capability, then we trigger the pipeline. We see that this is in pending state, we uncordon a single node, and we see that non-optimized workload gets scheduled on that particular node. By including the non-optimized workload, we aim to compare performance enhancements and platform utilization by platform-aware machine learning workload and platform-aware non-optimized machine learning workload. This step highlights the importance of not only having the special platform but also utilizing the softwares that are optimized to leverage the capabilities of that platform. Through this comparison, we can provide valuable insights into the performance improvements, resource utilization, and overall efficiency gained by our platform-aware machine learning solution. So now it's time to do the live demo. I will walk you through step-by-step workflow for the platform-aware optimized MLOps pipeline, and will showcase the platform aware MLOps pipeline and platform aware non-optimized MLOps pipeline run for training a model. So now I will start the demo. To do so, I need to take the RDP session. I will take the RDP session to my lab, where I can access the RK2 cluster, Rancher and GitLab and so on and so forth. So let me just connect to the GitLab. To begin with, I will navigate to the Rancher web UI dashboard. I will select the RK2 Kbench cluster from the list of the clusters. I will access the nodes details. So here are multiple nodes here. I just wanted to showcase that how NFD labels each node with its existing capability. Now here we can see that this node has multiple labels provided by the NFD. So here what we are focused on is hardware multi-threading, which value is true for ISEX worker 01. If I show you the node which does not have this capability, we will see that here is the value for hardware multi-threading capability is false. Going forward, I will cordon off all the worker node with the hardware multi-threading capability, following the flow of the animation in the presentation. So I will cordon off ISEX worker 1, 2 and 3 just because they have hardware multi-threading capability into them. Okay, so they have been cordoned off. Now I will trigger the pipeline from the GitLab dashboard for optimized MLOps workload. I will run the pipeline for optimized workload. Run the pipeline. Now we will see the workload section of the RK2 Kbench cluster. Here is nothing, but in few seconds there would be some. So I need to trigger the deploy job, then the workload will be deployed in the cluster. Just wait for few seconds, the workload will be here. Now it is here. If we go inside the details of this workload, we can see that there is no any node available for this workload, so that this workload can be scheduled and run on that node. Just because there is no any node in which hardware multi-threading capability available, this workload cannot be scheduled. But we have some other nodes, schedulable nodes, but this workload cannot be scheduled on those nodes, those available nodes. I will uncordon a single node with the hardware multi-threading capability. Its effects will be that the workload will be scheduled on that particular node exclusively. We can see its state. Now this workload is running on ISEX worker 01. So let's start the training of the model. To do so, I need a token. For that, I will run a command inside the container from the Rancher dashboard. I have got the token. I can now access the Jupyter notebook. This is the notebook, and for training the model I need to run all the cells of this notebook. So I will run all the cells, and now I have to just wait for its training to complete. Going further, I will also schedule a non-optimized workload. We will follow the same flow as we have done for optimized workload. So I will cordon off the node with the hardware multi-threading capability. I will go to the GitLab dashboard. I will run the pipeline for non-optimized workload. I will trigger the deploy job, go to the Rancher dashboard and see the workload section of the RK2 K-bench cluster. Let's wait for the workload to be scheduled. Okay, so it is here. If we go inside the details, we can see it is also facing the same problem that there is no nodes available into which this workload can be placed. Okay. Now I will uncordon one of the node with the hardware multi-threading capability. Uncordon ICX worker 2, see the workload status. If I go inside the details, I can see that this workload has been scheduled on the ICX worker 02. I will access the token by running the command inside the container. Now I can access the Jupyter notebook. Access the notebook, and for training the model of the non-optimized workload, I need to run all the cell of this notebook, and the model training will be start. Okay. The deployment process is completed. Now let me show that how these workloads are utilizing the underlying platform. So I will go for the TensorFlow workload which is optimized. I will access the metrics. I will go to the Grafana dashboard. We can see that the utilization statistic or spike is going upward for the optimized workload. Let's do the same thing for non-optimized one. Access the metrics tab, and from there I will access the Grafana dashboard. So nothing is there as of now. So we will just wait for the model to complete their training. After that, we will compare their performance enhancements and platform utilization. Waiting for model to complete their training. So both the model have completed their training. Now we can compare their performance enhancements, platform utilization, and overall efficiency. So let's do the comparison. I am at the Grafana dashboard. So these are the metrics for the optimized workload, where I can see that the workload has started its training at 12:24 and completed its training by 12:42, which means it has taken almost 16 to 17 minutes to complete its training. Its CPU utilization is about 206 CPUs. Now I go to the non-optimized workload matrix. Here we can see it has started its training by 12:26 and completed its training by 12:52, which means it has taken almost 28 minutes to complete its training. Whereas we can see that this workload cannot utilize CPUs more than 90. So this is what I wanted to compare. By this we present a end-to-end optimization for MLOps pipeline. Now I will move ahead with the presentation. So let me just go to the presentation. So we are at the use cases slide. So we can see there are few use cases for this solution. So these use cases can take benefits from our solution, where platform aware machine learning pipeline and optimization, image classification, natural language processing, speech recognition, machine translation, and recommendation systems. These kind of machine learning workload can take benefits from our solution. With this, we are at the end of our demo on platform aware machine learning, pipeline optimization, and performance enhancement using Rancher, RK2, and other open source technologies. We hope you found this session informative and insightful. If you want to discuss more on our solution, please reach out to us. We appreciate your presence here at SUSECon 2023 and look forward to discuss with you and collaborate with you. Thank you. Have a great day.